Hello, I am Yongwoo from Yonsei University. I will introduce my work, HECATE Performance-Aware Scale Optimization for Homomorphic Encryption Compiler. This work is collaborative work with Seonyoung, Cheon, Shin-Young, Changsu Kim, Eunkyung Kim, and Professor Dongyoon Lee and Professor Hanjun Kim. Various applications offload computation to the cloud services. But the application that uses sensitive data cannot offload computation because of privacy issue. For example, healthcare application uses sensitive data like personal medical data. Fully homomorphic encryption enables the privacy-preserving computation offloading. Fully homomorphic encryption allows computations on a ciphertext without decrypting it, hence sensitive data can be used without concerning the privacy issue. Recent advances in fully homomorphic encryption provides fixed-point arithmetic which is useful to build machine learning and deep learning applications. To build FHE program, the programmer should translate the normal program to use FHE operation and select FHE encryption parameters. FHE has constraints that affect correctness and security of the FHE program. The FHE constraints and the characteristics of FHE operation complicate FHE program optimization a lot. To meet the constraints and optimize the FHE program, the programmer should know FHE internals deeply. To reduce the programming burden, FHE compilers automate the program translation and optimization and encryption parameter selection. I will briefly introduce FHE background. First, FHE ciphertext has a scale parameter. FHE ciphertext encrypts a fixed point numbers in an integer with the corresponding scale. Because FHE ciphertext inherently contains an error, so scale should be large enough to hide the error. Scale parameter can be changed by FHE operations during the computation. For example, FHE multiplication multiplies not only the encrypted values, but also the scale parameters. Second, FHE ciphertext has a coefficient modulus parameter that limits the maximum size of scale. Also, a coefficient modulus parameter can be changed by FHE operations. For example, rescale operation reduces the scale and coefficient modulus in the same amount. The reduced amount is determined by rescaling factor and the coefficient modulus is a multiple of rescaling factor. The number of removed rescaling factor from coefficient modulus defines the level property of ciphertext. I will introduce a scale flow of the multiplication example. The rescaling factor is fixed as 60 for this example and the later examples. The maximum scale, which is defined by coefficient modulus, is 120. Note that y-axis represents scale in log. Initial scale of a root value x is 20 and the level starts from 0 for fresh ciphertext. After squaring the x, the scale is multiplied and results in 40. The multiplication does not change coefficient modulus, hence the coefficient modulus is remained as 120 and the level is also remained as 0. This more complex example computes x squared plus y squared and then square it. Same as x squared example, the coefficient modulus is 120 and initial scale is 20. The scale of x squared and y squared is 40. Addition does not change the scale, so the scale of z is also 40. Finally, the scale of z squared is increased to 80. Consider that if we apply rescale to the z squared, the scale is reduced by rescaling factor, so it is reduced from 80 to 20. The level of the rescaled z squared is increased to 1 because one rescaling factor is removed from coefficient modulus. Then the coefficient modulus is reduced from 120 to 60 because rescaling factor is 60. The operation that affects scale and coefficient modulus is called scale management operation. Another scale management operation is mode switch. Mode switch does not change scale, but it increases level. After applying mode switch to Z, the scale is not changed, but level is increased. FHE has constraints on scale, level, and coefficient modulus. The first constraint is that scale should be always lower than the coefficient modulus. If the scale exceeds coefficient modulus, the scale overflow occurs. Scale overflow invalidates the encrypted data inside the ciphertext. For example, the scale of z to the 6th is 120, which is bigger than the coefficient modulus 60. This computation is prohibited by FHE constraint 1. Because the ciphertext inherently contains an error, too small scale causes scale underflow. To prevent scale underflow, the scale should be larger than threshold called waterline. If the waterline is getting larger, the ratio between encrypted data and error is getting smaller. It means that the program is getting preciser. The waterline can be set by a programmer. In this example, the waterline is set to 20. The rescale on z cubic reduces the scale from 60 to 0, which is lower than the waterline 20. The rescale on z cubic is prohibited by FHE constraint 2, different from the rescale on z square. There are constraints for operands of binary operator. For any binary operator, the level of operands should be coincide. To match the level of operands, mode switch can be used. For example, mode switch on z increases level and it can be multiplied with rescaled z square. Addition operator has an additional constraint. To add two ciphertexts, the scales of them should be coincide. For example, adding z square and z, whose scale is 20 and 40, is prohibited by FHE constraint 4. In this case, we need to upscale the z square to 40 by multiplying 1 with scale 20. The example shows a legal scale management which satisfies FHE constraints. The goal of scale management is reducing the increase of scale. The lower scale reduces the initial coefficient modulus, which affects the latency of FHE operations. This example is neither scale optimal nor performance optimal. Existing work reduces the scale reactively by inserting rescale when it can meet constraint. Scale management with rescale and mode switch only allows to reduce scale as rescaling factor or 0. Reactive fixed factor scale management is not enough to achieve scale optimal. Moreover, optimizing scale does not directly improve the performance of the program, so the scale management should directly reflect the latency of FHE program. The first insight of this work is flexible factor rescaling. As shown in the example, proactive flexible factor scale management reduces the result scale. If the compiler proactively reduces the scale of z on level 0 by 20 instead of rescaling factor, the result scale is also reduced by 20. This example shows the need of a new scale management operation instead of mode switch. The second insight is performance-aware exploration. The operator latency depends on initial coefficient modulus and level of ciphertext. Because the latency is reduced if the level is higher, there is faster scale management option than the scale optimal option as shown in the example. In the scale optimal program, z square is calculated from z level 0 and then rescaled. Compared to the z square from z level 1, the scale is smaller. But the multiplication on level 0 is more expensive than level 1, so the latency is larger. Because finding faster scale management option is not straightforward, the compiler needs to explore the scale management space. Scale management space exploration with performance estimation allows performance optimizing scale management. This work proposes HECATE, performance-aware scale optimizing HE compiler. HECATE is the first work that proposes a new flexible factor scale management operation and a performance-aware scale management space exploration. HECATE first generates HECATE IR from Python frontend. Then scale management unit generator generates the scale management unit that groups the ciphertext to reduce the exploration cost. Scale management space explorer consists of three steps. First step is planner that generates scale management plan to optimize the scale. Second step is scale management code generator that instantiates scale management operations and meet the FHE constraints. Last step is performance estimator that estimates the latency of the program and then feed back the latency to the planner. The generated code from the Explorer is lowered to the code generation backend. The most distinct feature of the HECATE IR is newly proposed operation downscale. Downscale is a scale management operation that reduces scale by arbitrary amount. Downscale first upscales the ciphertext by multiplying 1 with arbitrary scale and then rescales it. By doing so, downscale reduces the arbitrary scale without breaking the FHE constraints. The program written in HECATE IR is preprocessed by Scale Management Unit Generator. Scale Management Unit is a ciphertext group that has the same scale and level. By doing so, the compiler does not need to handle every ciphertext in the program, so the search space is reduced. For example, the root value x and y shares its level and scale. The scale of x square and y square is different from x and y, so they forms another scale management group. From addition, the scale and level is remain same, but there is opportunity to insert scale management operation, so it forms another group. Then planner generates optimization plan. Optimization plan shows where to insert scale management operations. The example plan selects edge between SMU 2 and 4 and insert one scale management operation. Planner does not know the scales and levels of ciphertext, so it cannot determine which scale management operation should be inserted. Planner just specifies where to insert scale management operation. Planner generates a new plan from the previous plan. To generate new plan, planner adds one additional scale management operation. The example plan adds scale management operation between the edge between SMU 3 and 4. Because the plan is not guaranteed to satisfy FHE constraints, the program may need an additional scale management operation. The next step, scale management code generation, is responsible to meet the FHE constraints. Scale management code generation uses the newly proposed proactive rescaling algorithm. The algorithm instantiates the scale management operations from optimization plan and insert additional scale management operations to meet FHE constraints. For example, the scale management operation is instantiated to downscale for z level 0 and rescale for z square level 0. Because this program does not need additional scale management operation, the algorithm does not insert another operation. Finally, performance estimator estimates the latency of the generated program. Latency of FHE operators depends on the level and operator types. The estimator profiles the latency of operations for each level and then calculates total latency from the latency of each operators. The table shows the latency for each operations. From the profile, performance estimator follows the execution flow and accumulates the latency of the FHE operations. The total cost is 22, and then this information is fed back to planner to find the best scale management plan. We evaluate the HECATE on the machine with Intel i7 CPU and 64GB RAM. We use Microsoft C library as our FHE backend library. We compare 4 scale management schemes. Our baseline scale management scheme is EVA, which presented in PLDI 2020. Pulse scheme uses proactive rescaling algorithm without scale management plan generation or planner. SMSC scheme uses scale management space exploration but uses EVA as scale management code generation scheme for meeting FHE constraints. HECATE uses both proactive rescaling and scale management plan generation. We tested 2 image processing benchmarks, 2 deep learning benchmarks, and 4 machine learning benchmarks. EVA shows efficient result only for multi-layer perceptron, which has simple arithmetic structure. Simple arithmetic structure reduces the complexity of scale management, so the improvements from the proposed techniques are marginal. The improvement of parse comes from the reduction of the initial coefficient modulus. The initial coefficient modulus is affected by borderline setting and structure of the program, so it may fail to reduce the coefficient modulus. Note that the coefficient modulus is quantized by rescaling factor. Parse shows great improvement on Harris corner detection because it reduces the coefficient modulus as square of rescaling factor. The performance improvement varies among benchmarks because the improvement is getting smaller if the total size of coefficient modulus is getting larger. SMSE improves the performance by generating optimization plan that reduces the level of each ciphertext. Note that the SMSE is always better than EVA thanks to performance estimation. SMSE can reject the plan that is slower than EVA. However, the inherent limitation of EVA limits the performance improvement because SMSE uses EVA as the code generation. SMSE may find the plans that reduce the coefficient modulus like parse, but it is not robust. HECATE shows the best performance thanks to the synergy from parse and SMSE. The geometric average of performance improvement is 27% compared to our baseline. Additionally, we evaluate the search space reduction from scale management unit. Scale management unit groups the ciphertext and reduces the number of candidates where to insert scale management operation. By doing so, it can reduce the number of epochs to find the optimal plan and also the number of plan evaluated in one epoch. The image processing and deep learning benchmarks exposes a huge parallelism. The parallelism on benchmarks mean that there exists a lot of ciphertext that shares the arithmetic structure that defines the ciphertext. This characteristic reduces the number of SMU and it appears to huge reduction in the ratio. We find two major problems of the existing FHE compiler. First, reactive fixed factor scale management, and second, scale optimal is not performance optimal. HECATE proposes performance-aware scale optimization with proactive rescaling with downscale and scale management space exploration with performance estimation. HECATE achieves 27% lower latency compared to EVA. Thank you for listening.